Welcome to this solution video for Ducky'S pond. So there is a separate video which explains the problem and the interface and what you should do. So here I'm going to focus on doing one solution in Python, and then you would have to translate it to Java or C# or whatever you're writing the solution in. I was showing the problem. It's something like this, but let's move to the interface here and try to solve level 1. So in level 1 make move, we get duck degrees, duck distance, positioning the duck where we are currently, and then cat degrees where the cat is on the circumference, and then we should return a float for the direction we want to take for the next second. So it's divided into seconds. We have to also return a positive degree, or from 0 to 360, so we have to do modulo 360 when we return. Something I didn't really mention much in the explainer, but so how do we then solve level 1? Well, as I mentioned in the explainer video, what we need to do is to just find the opposite direction to where the cat is, and the degrees work like this. So this is also in the description. We have 0 degrees to the left, to the very right, and then it's increasing in value until we reach 360 degrees to the right again. So clockwise or anti-clockwise is positive here. So we can keep that one there. Or actually, yeah, let's do it like this. We also have that degree help here. So so what I do here is I set a direction on the class. So that variable I initiate with none, just to know that it is not initiated yet. And all we do here in the beginning is we check if we haven't set the direction yet. Then we set the direction to whatever the cat degrees is, minus 180 degrees, so the very opposite direction. And then we need to do modulo 360 just to make sure we are in the range 0 to 360. So this is the float modulo. And then we just return self-dot direction whenever we get called. And since when it's set, we're never going to change it. We could look at what happens if we set it at every second, and that will not look as good. But then let's see how we solve this in the canvas. Yes, we just head straight for the opposite direction and we beat the cat by 2.4 seconds, like so. And if we would always set the direction instead, let's see how that looks. Meaning we always go in the very opposite direction. It starts to look good, but then it makes us go in kind of a circle, because we're always moving away from the cat, and since he's very fast, we start to go away from him like this, and then we reach the 300 move maximum. So the way to go is to just set the direction once and then go in that direction for level 1. So that's cat speed 3. Now let's go to cat speed 4. So here instead we need to do something more clever. So if I'm first going to explain the solution a little bit, maybe on my drawing that I have here, what we want to do is we want to go with, I'll remove a little bit of the drawing we had before. And what we want to do with as the yellow one, the Katniss, we want to find a circle where we are still faster than the cat. So there's a little bit of math behind that. We can check how that looks. But yeah, so one way to say it is that the circumference, the length of the circle, the circumference around it, should be less than 4 times the circumference of the big circle, because that means we are in an even pairing. So then we could move around the circle once in the same at the same time as the cat moves around the big circle. Yeah, I should change this also for level 2, which we are doing now. It's not 3 meters per second, then it's 4 meters per second here for the cat. So we basically, the formula we have is whenever the smaller circle, we need to find a radius where the smaller circle is slightly less than 4 times, the circumference is slightly less than 4 times, or slightly less than a fourth of the circumference of the big circle. So first we can use an equality, and then we reduce the size of this inner circle a little bit. So and then we just go to that circle, we start moving around until we find ourselves in roughly the opposite. So yeah, the cat will follow us, and then we find ourselves in roughly the opposite direction from the middle. So the middle point should be between us and the cat, and then we start to dash for the edge. And one realization when I solved this also was we can, when we find ourselves on the opposite from the cat, maybe here, then we can start to dash immediately for the edge there. But actually it's slightly better to do it at a tilt, it turns out. That's a bit of trial and error. So then we'll find ourselves here, and hopefully the cat will be, well, will be trying to dash for us, but it will be missing us by some number of meters there. So if we go back to the interface here and look at the code to implement this, we're now in level 2 make move. Yeah, and I'm doing this in Python, as I said. If you switch here to C#, then you get a different starting code. If you go to Java, you can do it in Java, but we're going to focus now on Python and try to explain the algorithm, and then you can do it in whatever language you want. So first we set some constants here. We can look at this later. There is a target distance. That's actually the calculation that I just talked about. So it means that at 11 meters that's the radius that we want to achieve, slightly outside of this white circle here, the inner white circle. And at that point, at 11 meters, we are still faster around the circle than the cat is on the bigger circle. So I'm not going to show that calculation now, but we can also do it via trial and error later. So that is the target distance we want to reach, the radius we want to reach before we start to go around in a circle. Okay, so the pond radius is 50, just a constant, it's a given. Then we have a degree threshold. We're going to look more about that later, but since we're doing this on the scale, we are getting 1 second per move. We can only move in straight lines for every second. Then we need to, it can be a little bit jiggly at times, so we want to, maybe we'll not find ourselves in exactly the degree where we are opposite of the cat. So we want to have some little wiggle room there of what's good enough for us to start to make a dash for the edge. And then tilt degrees is the thing I talked about at the end, where we can beat the cat by a little bit more if we slightly tilt the angle, what I showed here. We tilt the angle a little bit from where the direction the cat is going, so then we can beat the cat by a little bit more. That's the tilt degrees. So here is an internal function, should move clockwise, but let's go first. We'll return to this one. So first we have we are setting a stage here, so self.stage on the class. So stage 1 is simply moving to the target distance from the midpoint. So this is where we want to go before we start moving in a circle. So first we just see that if we are in stage 1, the beginning stage, and we haven't found ourselves at the target distance yet. Here we set a super small difference here, since we are comparing floats, so we can't do an exact equality. But and this number is very, very small, but it also, because we know we're going to move 1 second per move, and that means we are going to find ourselves at exactly 11. If this number would have been chosen to be 11.3, then this number would be far too small. That would be a problem. So yeah, we can use 0.01 as a little difference, because we know we're moving 1 meter per second. So we will find ourselves at exactly, or very close to exactly 11 meters from the midpoint. Since we're using floats, it cannot be said to be exactly 11.0. So this is the comparison we do to see, have we found ourselves at the right radius to start going around in a circle. And when this happens, we set self.stage to 2. So then we just have some degrees to start with here. We return self.direction, So self.direction is set to none in the beginning here. I'm just seeing where do we set self.direction for the very first for stage 1, so to say. Interesting. Aha, yeah, here we are doing it. Okay, sorry. So in the beginning here we are doing some checks on whether we should move to the next stage, and then we have an if statement here which carries out the code for the stage we are currently in. So yeah, maybe we can jump to this part of the code now. So we are in stage 1. We haven't found ourselves at distance 11 from the midpoint yet. Then what we do is, if we haven't set the direction yet, we just set the direction to whatever the categories is, minus 180 and modulo 360, like we did in level 1. We just start going in the very opposite direction, because why not? It's a good initial try, so to say. So then we're going to go to 11 meters from the midpoint in stage 1. At some point we reach 11 meters here, then we go to stage 2. So when we are in stage 2, we come to this code here. So this is the more complicated part. We want to move in a circular fashion until we are 180 degrees away from the cat, as it says. So then we're going to use this should move clockwise direction. So this function is testing whether the cat wants to go clockwise in this direction or anti-clockwise this direction. And this gives us the sign, because we want to reach the opposite side of the midpoint as quickly as possible, to be opposite of the cat. So this should move clockwise checks the categories and duck degrees that we get in. We calculate a diff here, a value of the difference between duck and cat. And if it's less than 0, then we change the duck degrees, or the degree diff, to duck degrees minus categories minus 360. Yeah, this is just to get a positive value. I wonder if we could have just used modulo here. But this is when we realize we have a negative value, then we want to move to the positive side. So then we do this. This might be possible to simplify. And if degree diff is less than 180, then we return false. Then the cat should move anti-clockwise. And if it's between 180 and 360, then we return true. I'm probably saying this wrong. Should move clockwise is what we should do. As a duck, we should move clockwise around the inner circle here. So from this should move clockwise, we get a sign. So -1 if we should move clockwise, else 1. And then we use that sign here. So what we do is we set the direction to whatever the duck degrees is currently, plus sign times 92. So we're basically maybe it's easier to do this on the whiteboard here. So basically we are saying something like this. If we are, let's do it on a new one actually. Let's draw the pond again. This is a midpoint. So if we are here, some 11 meters from the midpoint, then we are given the duck direction is this direction here. Let's say, what could this be? Let me look at the... this could be something like 150 degrees maybe. So then we want to instead move in a circle. So how do we find a circle? When then we want to move something like this, like perpendicular to the direction that we are from the midpoint. So then we take 150 minus 90. Let's do it like this. So this is something like 60 degrees. And if we look back on this one, or we can look here actually. So 60 degrees is something like that, going in that direction there. So that is 90 degrees difference from 150, if that's where we are right now. So that's why we do -90 and get the direction which is perpendicular to our direction from the midpoint. This means we will always move in a circle. I'm saying it now, and maybe it's complicated, but we'll also see it carried out once we run the code. So first I'm going to explain the code, and then we're going to see it actually happening. So that's what we're doing. Let's see. Yeah, so we do plus sign. And why is it 92 then and not 90? Well, this is to make up for the fact that we're only getting to move, choose the direction to move every second. So if we got to choose where to move every 1/1,000,000th of a second, then this would be basically 90. But this is, we're going to see that this works. In the end, I did this more by trial and error than maths actually, but 92 is enough to make sure that we move. Okay, if I'm going to explain this again on the whiteboard. So if we would use 90, let's say we're moving on the outer circumference here, it would put us slightly outside of the circle all the time. So instead what we want to do, if we are here, we want to move to here. So we are moving in some kind of like a dodecahedron or something, like a inside of the circle. So this is because of the problem that we only have 1 second per decision. That's why it becomes 92. We can maybe look, if I remember, we look at changing this and see how it changes the movement. Okay, and then we do modulo 360 because we're required to return a value between 0 and 360. This is stage 2. Yeah. Maybe we can, what we can do is, let's just look at that part now. So I'm going to return an invalid value here just to show you where we are so far, because we're doing two things already. We're moving to that circle 11 meters away, and then we're going in a circle until we find ourselves opposite of the midpoint from the cat, or close enough at least. So since we only have, you can see, we can only make a decision every second, so it's not going to be a perfect linear movement or continuous movement, but this is good enough. So this is where we want to make a dash for the end here. So let's go back and look at this more slowly. So in the beginning we're just moving out here 11 times until we reach 11 meters from the midpoint. Let's see, one more move. Yeah, so now we're 39 meters away from C, meaning we're 11 meters away from the midpoint. So now we go to stage 2. Now we say that, okay, now we're close enough to 11 meters. Now we go to stage 2. So now we just start to move around the circle, in a circle around the midpoint, and trying to be opposite of the cat. So let's look at that. Now is where we do minus 92 every time. So we move in a circle, and you can see now that now we are slightly faster than the cat at 11 meters. The C is going to move quicker than the cat around the circumference. Let's look at that. We can see it also here that the cat has an increasing number of seconds to reach C. So now it's 31, 31.1. So we gain something like 0.1 to 0.2 seconds for every second. And in the end, that's going to mean that C is... let's see, this takes some time actually, because 11 is pretty close to that limit, which is also a good thing, because then we have shorter time to make the dash in the end. And now you can see one interesting thing that's happened also, that this one is increasing all the time, but it's still under 38.2. So if we would make a dash now, we would miss it slightly. At least if we went in a straight line towards C, we would miss it slightly. So we're trying to get to where this number is higher than this number for Ducky, and it will happen eventually. So now you can see, now we are 0.1 second in favor, but of course now we're actually very close to start making the dash, and we reached 38.2, and here we are basically opposite of the cat from the midpoint. So here is where we want to make the dash, starting stage 3. But I did an error here just to be able to stop, because I want to show the code first, and then we see how it plays out in the canvas here. So stage 3, we have a check here then. Yeah, so here we are checking when we should go to stage 3. So there we are saying that, okay, we are at stage 2 if you're going to move to stage 3. And the difference, so we take duck degrees minus 180. So we're trying to see if the direction opposite from us, so we take our degrees minus 180, then modulo 360 to get a positive number. Actually, that's not, yeah, okay. We do that. And then we take that minus the cat degrees. So meaning if our opposite direction in degrees as compared to the cat degrees is under some threshold, and the threshold we set here is 5. If we set it too low, it will never occur. Maybe I can show that. If we set it to 1.0, I'll show you what happened. This will look really stupid, because now probably it will never happen. So we start to jiggle. It's fun showing this actually. Yeah, now we start to jiggle because we never reach that perfect opposite direction. And then we run into the 300 move problem. So that's why we don't have 1, but 5 turns out to work. I mean, I've done this by trial and error. We only have to get it to work once actually, even though it's fun to perfect it. So that's what we're doing here, checking versus that degree threshold. So now we know we are opposite of the cat. Then we go to stage 3. And we start off by setting direction to none, because we're going to set it again now. Actually, we don't have to do that anymore, I realize, because I'm using a base direction now. Yeah. So what we're doing, we have the direction on the class. We also have a base direction, which I'm going to show now. When we go to stage 3, here, we check if self-base direction is not set yet. Then we just calculate base direction to be the opposite direction from where the cat is currently. So in the end here, at some point when we are jiggling, let's say here, then the cat direction is up, maybe some 90 degrees, and we want to go then in about 270 degrees. And that we calculate here. So we take cat degrees minus 180. So 90 minus 180, then we'll get minus 90 degrees as an example. And then we do modulo 360, so then we end up at 270 degrees. So then we have the self direction, the base direction here. And then we have if true, yeah, because I had this, I changed the code just recently. And then every time we end up in stage 3 here, we're gonna check the sign. So basically now we want to apply the tilt. That's what we're doing. Maybe we can, I can write that here. I can show you how it works without the tilt. Apply a tilt to beat Katniss even more. Because this is not necessary. We don't have to apply a tilt. So if we skip that part and just do it this way, so we set the direction to the base direction, then we don't have a tilt. Yeah. This thing here is something old. It's not being used anymore. Okay, now we run the code. So now we're just going to carry out step 3 here without a tilt. And you saw the confetti. We did solve it now. So we're moving in a circle in stage 2. We find ourselves sufficiently in the opposite direction of the cat. And then we just make a dash for the edge. And as you see, we beat Katniss with 1 second. But if we think this was a lucky stroke and we want to beat Katniss by more, I mean, 1 second is logical, because if you look here when we start to leave stage 2 and go into stage 3, here the difference is, yeah, it's actually increasing here. So now the difference for us is 37 seconds, and with the cat is 37.3. I can't fully explain why it grows to... Aha. No, I don't know. I don't know exactly why it grows to 1 second right now. Maybe figure that out later. But you can see here it's slightly growing for some reason. It's a little bit strange actually. Maybe it has to do with the one that we do carry this out just every second. Yeah, anyway, in the end here we beat him by 1 second. And if we want to increase this number then, then we can apply this tilt here. So what we do then is in every step we check if the cat is going clockwise or anti-clockwise around the circle. This is the sign we get. It's similar to what we did before. We use this should move clockwise function we have and set the sign to -1 or 1. And then we set the direction to the base direction plus this sign times the number of tilt degrees. And then we do modulo 360 to get back to a value between 0 and 360. Yeah, this was without the tilt. Can remove that part. So this is with the tilt, and the tilt value I've also tried out by trial and error. So 75 works well, for example. So now we'll see how the tilt works. If I run the code again. Yeah, we saw the confetti. See if we can beat Katniss by more than 1 second. Yeah, we could. So now we beat Katniss by some 6 seconds. So it's almost 6 times better. And as you saw, instead of going straight from the cat, we're tilting it slightly. And it turns out that the difference in distance for us as the duck is only slightly more, but it's more, even more for the cat. So that's why we gain from this. Yeah. So this is the Ducky'S pond puzzle. And I can just show also if we start to solve level 1 by using instead level 2, then we are doing something even more optimal. So let's go back to level 1 first and just run the code we had and see how much we beat the cat with. We beat it with 2.4 seconds. But let's now use the level 2 strategy in level 1 by calling level 2 here. And we do that. Then we're going to go in a circle again. And there you see a little bit of jiggle. So that has to do with that we only get a decision per second. But it's actually in our benefit. So instead of 6 seconds, it's now 24 seconds. So a lot better than before. Why did it start to jiggle? Well, the thing is that at this point, for some reason in level 1, we just happen to be more perfectly placed on the opposite side of the midpoint. So when we start to move in a certain direction, the cat decides to go maybe anti-clockwise because it's closer here. And then we change the tilt to the other direction, and that's enough to change the cat's decision to go instead clockwise. And then that thing repeats for a number of times here. So since we are tilting it also, it changes the cat's decision. But we basically gain a little bit from that, so it's just to our benefit. It just looks very, very awkward or it's jiggly in the interface. But then it starts to, at some point here, it will have decided that, okay, so going clockwise now is the closest thing. Yeah, we don't get to reach the very end like that. So now it starts to do clockwise, and we apply this tilt of, what was it, 75 degrees, moving 1 meter per second. And as you see here, we will beat the cat by some 24 seconds. Cool. So that is the Ducky'S pond problem, and one way to solve it in Python, which you can apply to any language, of course. I think it's a very fun problem, so good luck solving it. Okay, so here is the calculation to see what distance from the midpoint we can still be faster than Katniss at. So if we have let's draw the pond over here. So we know that, yeah, this is the midpoint. We know this distance is 50. And then we're going to use Ducky'S distance, where Ducky is still faster than Katniss, like so. We know Katniss is always at distance 50. Then we just we calculate the circumference of the inner circle circumference. Then we have that as 2 times pi times the radius, which is d. And then we're gonna scale it with the speed of Katniss. So k is equal to Katniss speed, which is in meters per second, like so. So we have to increase or scale the length of the inner circle by the speed k to find the equality, where it's equal to the outer circumference, like so. And if we then calculate d, we can divide both sides by 2 pi, so we get d is equal to 50 divided by k. So this means if k is equal to 4, then that gives us d equals 12.5. So that is the acceptable circle that we can use. And for k equals 3, the level 1, then if we want to use the same strategy of going to this circle and until we are at the opposite side of the midpoint, then we would get a diameter of 16.7. So basically what we would use here is the 12, so that we are faster. 12.5 would be the equilibrium, 12 would make us faster, and 16 would make us faster for level 1 when cat speed is 3. So if we go here, we can try that out. In level 1, we can set it to 16 and use this strategy, and if we run, then we get something like this. So now it seems C is this distance from C is increasing, and then we make a dash for it and we beat Katniss by some 24 seconds.